Hello, everyone, and welcome to our summer 2020 webinar series. My name is Jim Shaw. I'm the Director of Sales and Marketing at DTS. Today's event is Navigating Real-World Test Setup Decisions, where we'll focus on some of the unique challenges of dynamic testing in extreme environments. Before we get started, I'd like to cover the format and a few logistics. The webinar will be a slide presentation with audio and video from the presenter only. You'll have the opportunity to ask questions by clicking the Q&A button at the bottom of your screen. We have a panel of our experts monitoring and answering the questions throughout the webinar, so feel free to ask questions along the way. We'll try to get as many answered as we can during the webinar, and we'll open it up for questions at the end. Scan the open question list and try to answer as many as we can get to, time permitting. The session will be recorded and made available to you at a later date to share with your colleagues. If there's a specific topic that you'd like to cover directly in more of a private meeting, please reach out to us and we'll coordinate with the appropriate salesperson and or support person and set something up with you. We're interested in learning more about and helping you solve your particular application challenges. So with that, your presenter today is Mike Beckage. He is one of our co-founders, and he runs our support organization. With us as well on the panel, answering questions in the background, is Kate Martin. She runs our support operations in Europe. And John Moores, who's an application engineer at our headquarters in Seal Beach. So with that, I'll turn it over to Mike.
Well, hello everybody, and good morning, good afternoon, or evening, depending on where you are in the world. And here we are in the DTS Zoom room in Southern California with another of our webinar series. And I'm really excited to have you here today. And it was a difficult topic trying to narrow down our subjects to just a few sort of key points today. I want to remind everybody that DTS has a really wonderfully done online help center. And if you go to our website, dtsweb.com, and click on the help center icon on the right, you can actually search for presentations like this. You can also do a text search in the help box, and you can dig up a lot more detailed information that will help bolster your understanding here. So I'm going to touch on this again at the end, but I want to remind you that I'm going to mention some things, and I'll say, hey, if you want to know more about that, go to our help center, which is a really good tool. So this, as Jim said, is we've done several of these webinars so far to try to stay connected in the COVID-19 world, and we will definitely do more. Today, we're going to be talking about navigating real-world test setup decisions, and I had a hard time really figuring out what to put in here that was only going to take 45 minutes. So what I'm going to focus on today is actually some of the most frequently asked questions we get have to do with how does the way that data acquisition systems are built actually relate to making sensor setup decisions? So I'm going to go through a little bit of a review of our architecture. We're going to talk some very specific sensor interface knowledge that I think everybody should have to become their own expert. And then we'll just touch on some other topics that have been covered in somewhat greater detail in the Principles of Dynamic Data Collection webinars that you can, as Jim said, go download and review. So, starting with the fact that DTS is a manufacturer of data acquisition systems like the Slice Pro and the Slice Nano, 12 channels in one hand, 18 channels in the other. It all starts for us with a data acquisition system where everything is in one small package. And what you're going to do is you're going to connect various sensors to this system, and you're going to connect a PC to the other side and communicate with it via Ethernet or USB. And what you need to know is how to make it take best advantage of the hardware. is really what we're talking about. So recapping from the Principles of Dynamic Data Collection seminar, this is a list of the steps to success that we discuss in that course, starting with, making sure you understand testing requirements before you actually try to set the system up. At the top, the first 4 bullet points there, I'm going to assume you've already done that. You know what tests you need to perform, you know what the requirements are, you know what measurements you need to take, and even the data bandwidth, and you've got the appropriate sensors. Now you need to figure out how to set up the sensors, you need to figure out how to set the data recorder to capture high quality data. And again, all this is covered in the 2 webinars we did, part 1 and part 2, Dynamic Data Collection, which you can get from our website. So a little bit of a review here. All of the data recorders that we sell have an architecture that looks like this. We have what's referred to as an analog front end that has an excitation or power source for the sensors. It's got a very special amplifier, and it's got some diagnostic features. We apply offset and gain, we filter the data, and then we digitize it. What we're going to focus on today is really some of the details of the analog front end that you need to understand in order to make proper setup decisions for just about any kind of sensing input. And we're also going to touch on recommendations for sampling rate and avoiding sampling error and things like that. So those are the 2 areas, key areas we're going to focus on today. So zooming in on that analog front end, basically it has several components. It's got the excitation source to supply power out to the sensor. We call that excitation, but it's a power supply. So we've got to be very accurate, and we have to know its voltage. We have an amplifier in that analog front end. It's a very special amplifier we're going to talk about. It has the ability to dial out or null out the offset from sensors, which are never perfect. And then we have a shunt check circuit that can apply a known amount of electricity or current to that sensor to make it move a certain amount so we can check it out. Now, underlying at the heart of the analog front end is an amplifier we call a differential instrumentation amplifier. This is a very special type of amplifier, and we're going to talk about why it's special. But the bottom line is it has a power supply, it has what's called a reference voltage, and it takes whatever signal appears between the plus and the minus input, and it turns that into an output voltage that has been amplified, that we can then pass along to the filters and then store it as digital data. If we take a closer look, and don't worry too much about the math here, but John Moores, who works for me here in California, is putting together a very detailed article for our help center that has all of this information. But the bottom line is, in a typical, let's say a slice nano system, it's basically a 0 to 5 volt system. So the amplifiers work on 0 and 5 volts, and then all of the signals are actually referenced to the very midpoint of that 0 to 5 volt range. Now, that amplifier has some special properties. The first one of those is actually what's called the common mode range. The common mode range is actually the range at which the amplifier will linearly amplify and pass those signals along. So the first point is, in the Slice Micro, Nano, and IP68 systems, and also Slice 6 and Slice 6 Air, we need to keep all of our signals within that common mode range. If we go beyond that, we might get clipping or lose data or have data distortion. So we need to stay in that common mode range. Now, there are some nuances. In a Slice Pro system, the common mode range is actually much larger. And we have an article on the Help Center that actually has a table showing all of the common mode ranges for those amplifiers. Why? Okay, the next thing is, what about the differential input range? This is the range of signals that that instrumentation amplifier can handle. And typically in these small low power systems, it's plus and minus almost 2.5 volts, not quite. Some systems actually handle more than that, but this is a baseline using our very smallest, lowest power system. And finally, the amplifier will have an output voltage. This is the same as the analog to digital conversion range. So all the systems have an analog to digital converter that if you review principles of DAS, we take continuously changing signals and we digitize them into steps that represent the voltages in time. So this output range here has got to be the same as the A to D converter range. If we look at this as a graph, and again, don't try to read all the numbers too much here. This is available on our Help Center. This actually shows you graphically what we're talking about here. All the signals you measure have to be within that common mode range on the left. And within the common mode range, the amplifier multiplies the difference between the plus and the minus signal and places those at the halfway point of the analog to digital converter. So for example, in an angular rate sensor, if it's an 8,000 degree per second angular rate sensor like this one here in my hand, and we plug it into the data recorder, this sensor will nominally have plus and minus 2 volt output. Plus 8,000 will be plus 2, minus 8,000 will be roughly minus 2. All those signals need to stay centered and within that common mode range. That's what we're talking about. So some important points when you're connecting sensors to your data recorder. And again, I want to say this is general information. We do things in a way that is relatively common with high quality data acquisition systems. So this applies to just about anything you're doing. Number one, the plus signal and the minus signal must be connected to something at all times. You cannot simply connect a signal to one of the inputs and expect it to work. Both of those inputs need to be terminated, and we'll talk about what that means with sensor setup in a minute. Number two, all of the input voltages must be within the common mode range. So in this case, with a slice nano or micro, it's got to be between 0.1 and 4.9. And then the output signals must not exceed the ADC signal range. So in these systems, it's generally 2.5 volts is the halfway point, and we can handle signals at a very minimum of plus and minus 2.4 volts. Key takeaway here, though, is got to connect both inputs to this thing properly. So let's take a look at a slice micro, and if we zoom in on the 7-pin connector that we use all the time for sensor inputs, we've got a plus and minus excitation and a plus and minus signal. We have a ground or shield connection, and then a place to hook up a maximum sensor ID chip. Now, the common mode range in this device, again, is 1 to 4.9, 0.1 to 4.9. The maximum differential is plus or minus 2.4. And this is important to note that all signals are measured with respect to minus excitation, which is effectively ground. So sensors, why is all this important? Why am I spending so much time on the differential amplifier? Number one, sensors come in lots of different configurations. The most common is the Wheatstone Bridge, which we'll touch on in a moment. Then there are active or amplified designs, voltage sources from all over the place, everything from millivolts to hundreds of volts in an electric vehicle. And then we have special sensors like thermocouples, RTDs, IR tracks if you're using crash test dummies. And then, of course, there's some other sensors like IEPE that we support as well. So in order to understand how to make proper setup decisions, you simply must understand the electrical design of the sensor and how it relates to the architecture of the data recorder. Let's start with the most common, often referred to as the Wheatstone Bridge. It's generally attributed to Charles Wheatstone from 1843. There's a lot A lot more information about this in our Principles of Data Acquisition webinar if you want to look at it. But basically, it's 4 resistors put together in a diamond pattern. We apply an excitation signal, and basically we apply any excitation, generally between 2 and 10 volts. We create a small voltage across the bridge when we put mechanical stress on it, and that signal is amplified, filtered, and recorded by the DAS. And important point is the output is proportional to excitation. The more excitation we put in, the more voltage we get out for a given mechanical excitation. So we can also call this a resistive bridge input, but this is exactly what our systems were designed to measure routinely. They're perfectly designed for handling any kind of bridge that you can imagine. In this case, you simply connect the 4 wires of the bridge, and then the settings, this might be an accelerometer or a strain gauge load cell, you simply pick the right parameters in the software. And so basically you can use any excitation voltage that the DAS has available, but remember that piezo-resistive bridges should be calibrated at the voltage you intend to use them. If you have a slice nano system, it only has 5 volts excitation. That is its only choice. If you have a slice pro system, it will do 2 volts, 5 volts, and 10 volts. So you've got more choices, it's a bigger system. If you're going to use accelerometers with a slice nano system or whatever, they should be calibrated at 5 volts. This is a very key thing and often missed in this world. So if you're buying this system, specify from the manufacturer a calibration at 5 volts. These are full bridges. As I mentioned, the output's proportional to excitation. You generally want to remove the offset. You can zero it just about any way you want. And yes, please use the shunt test. So let's talk about amplified sensors like the angular rate sensor. So although it's a tiny device, smaller than my fingertip, it actually has a sensing element that uses what's called microelectromechanical system technology. It also has a built-in power supply, amplifier, and filter. And so it does something much different than a bridge in that we can put in a very wide input range of voltage, and then we get out a calibrated nominal plus and minus 2 volt signal. For the ARS 8K, it roughly puts out 0.2 millivolts per degree per second, and that adds up to roughly a 2 volt output. So let's talk about what that means. There's a class of sensors called active sensors with 4 wires. So this is a perfect example. The blue box on the left indicates that we have a sensing element depicted by the yellow X. We have some active circuits inside the box that are run and excited by the excitation source. And then the output of that device is typically centered at or near 2.5 volts. In the case of an ARS, our reference voltage that comes out on the plus signal is 2.4 volts. And then as you turn the device left and right, you will get a signal that varies right around 2.4 volts. So at rest, it'll give a 0 differential to that amplifier. We turn it one way, we'll get a negative differential, and the other a positive. There are a whole class of sensors out there like this. Now, additionally, if we take a look at the sliceware setup here, you see some these are the questions you need to answer for making setup decisions. Number 1, all the serial number is of course important, but the sensitivity, the excitation voltage, the range, is it a full bridge, half bridge, or whatever? We want to perform a shunt test, and we want to use the equivalent resistance, which if you look at a cal sheet for an ARS, it's 3,000 ohms. We want to check the offset, we want to remove it, and then you can zero it a couple of different ways. In this case, I'm saying, zero it when it's at rest. Now, there's another class of sensors that are called active sensors with 3 wires. These devices typically take the same 5-volt excitation, and they have a single signal output. And what do you do with that? We're often asked, how do I hook that up? And a lot of times people do it wrong. Now, because of the architecture of our system, we actually have what's called half-bridge completion in our systems. We have a 3,000 ohm half bridge inside, and when you select half bridge in the software, it actually connects the output of that half bridge to the positive signal. Now, why do we do that? There's a little bit of a legacy reason there, in that many sensors over the decades have actually worked this way. And it doesn't really matter because the amplifier simply multiplies the differential. It's important to note, though, that in our systems, when you turn on half bridge, it goes to the plus signal, which means you do not connect the plus signal with a 3-wire active sensor. Also, the shunt circuit, which takes a precision voltage and converts it to a current, goes into that same plus signal lead. Now, the beauty of this is with a typical 3-wire active sensor, you can use 5 volts or 10 volts excitation. You can tell it it's a half bridge. Generally, these are not proportional. Offset removal depends on the type, which we'll discuss in a minute. And then, yes, please use the shunt cal. When you use the shunt test, you simply put 3,000 ohms into the appropriate window in the software. Now, what about floating signal source? Sometimes we're asked, hey, I've got this thing that generates voltage and it's just out in space. And like examples of this might be a heat transfer gauge or a battery-powered sensing system, probe, like a temperature probe. Well, again, you make use of the half-bridge completion. You simply connect that signal, that floating signal, to the plus and minus signal, turn on the half-bridge. The excitation really doesn't matter. These are generally not proportional to excitation. And again, the offset and zeroing will depend on the type of sensor. You cannot test these types of sensors. What about a grounded signal source? Sometimes we have a box that shares a common ground with the data recorder. In that case, you can simply connect those common grounds together. You can use either the shield, we recommend using the shield pin connection for that. And then the plus signal output from your grounded signal source actually has to go to the minus signal input, and we turn the half bridge switch on. Now, an important point here, the amplifier doesn't really care what polarity of signals it has. It just amplifies the differential. So if you want to make the signal go the right direction, in this case, you simply turn on the inversion. There's a checkbox that says invert. You turn that on, and you'll get the right polarity. Now, what about measuring really large voltages? In the world today, we have an increasing use of high voltage battery systems for electric and hybrid drives. A lot of times, people will want to measure those voltages. Or let's just say you want to measure the voltage from a typical car battery at 12 volts. Well, that voltage is beyond the common mode range of the amplifier, and so we use a simple circuit that we call a range expander. And the range expander is basically a 10K ohm bridge with added series resistors. You can see here the 50K series resistors mean that the input is safe to measure plus and minus 20 volts. The beauty of using this methodology is it's ground agnostic. You can ground either the plus or the minus inputs and it still works. We actually sell a gadget called a range expander that has these 6 resistors actually built in to the back shell of a connector. So you just plug it in, you get 2 wires, and now you can safely measure larger voltages. We have those available up to 800 volts. So let's talk a little bit about some special sensors. In this case, thermocouples. Well, thermocouples fall into a special category of three-wire active devices. Typically, we use a thermocouple adapter externally, and it takes plus and minus excitation, and then it has a single output that needs to go to minus signal with the half bridge switch turned on. We have a very detailed article on our Help Center. There's a link here in this slide, but if you literally go to the Help Center and type in thermocouple, you'll find the data sheet for the thermocouple adapter. You'll find the setup recommendations for thermocouples. Let's talk about another device, resistance temperature devices, or RTDs. They're not super commonly used in our world, but if you want to hook up an RTD, we have a really, really detailed instructional article on our Help Center. So again, simply go type into the search box RTD, and you'll get a diagram, which is basically how you hook it up to the data recorder. You'll also get an Excel spreadsheet that helps you understand with your particular RTD how to put the parameters into the software. So an RTD, if you're not familiar, is typically a platinum device, often called a PT100 for platinum 100 ohms. They can come in surface mount devices and probes, and generally very accurate and can be helpful in extreme testing environments. Let's talk about sensor checkouts, and this is actually a slide taken from Principles of Dynamic Data Collection. And in the green there, number one, I'll start with number one, never assume that everything's working okay with some kind of empirical check. Use shunt checks whenever possible. And we've done our best to make it possible to use these easily in our systems. We have ways to measure the bridge resistances, and it's very simple and automatic. Apply a mechanical excitation, right? If you have an ARS, rotate it. You have a pretty good idea of how fast you can rotate something, right? If it says 50,000 degrees per second when you check it out, it's probably wrong. And then finally, understand the data channel diagnostic information. This again is covered in the other course with a lot more detail. So let's talk a little bit about resonance and range choices. Many sensors, especially undamped accelerometers, have resonant frequencies at very high amplitudes, at very high frequencies. And I have an example of this in a minute, but this resonance can induce all kinds of errors, including overdriving the front end amplifier or simply becoming nonlinear. The problem looks like this, okay? This is an actual look at what the sensor resonance out of a 2000G undamped accelerometer looks like. The blue is actually very high frequency ringing, and when we put a filter on it, the magenta line is actually the data we care about. And so in this case, the data we care about was, maybe 200 Gs at the most, but we're actually seeing almost 3,000 Gs peak to peak of information there. So the key takeaway there is we need to set the DAS to a much higher range than we might expect to measure. Let's take in a real-world example here. This is an impact test using an accelerometer on a mechanical impact. And when I filtered the data at the frequency that I'm intending to use for my data analysis, I'm getting roughly 30 Gs. This was a very, let's call it a severe impact. And I would say, well, gee, if I set my range to 50 Gs, that would be more than enough. But what happens when we remove the software filter, we can see that we have ringing at roughly 200 Gs peak to peak. This is real data. There's nothing wrong with this data. And the fact that we filter it and see this tells us something very important. If we're doing a crash test or something that's a destructive test, we need to be very careful in setting the ranges. We set a range too low. If we saturate the amplifier with that signal, then we'll no longer get valid data. Well, let's talk about bandwidth filtering and sampling. Number one, we talk about the sampling rate as in samples per second. And that sampling rate is designed, or we should be designing it, in order to record a data bandwidth or the bandwidth of interest. And the bandwidth of interest is the range of frequencies over which we need accurate linear data. If we're doing something like automotive or aerospace crash testing with test dummies, then it's very common that that bandwidth is DC, or from 0 hertz to 1000 hertz. There are actually a lot of requirements for data bandwidth and sampling. If you're using the SAE J211 or ISO 6487, the required bandwidth is what's referred to as class 1000, and the minimum sampling rate is 10 times that 1000 hertz. The next version of SAE J211 will in fact require 20,000 samples per second. Now, this is the key takeaway here, is that the bandwidth of the data that you're trying to collect has to be appropriate for the application. For example, automotive and aerospace human safety testing almost always requires SAE class 1000. Acoustic or high frequency things like blast pressure measurements, military testing and all that might have much higher bandwidth requirements. We're doing some work in soldier protection where that bandwidth of interest is 0 to 20,000 hertz. What about material properties? I'm testing, metal under, high rate loading, or validation of finite element models sometimes require high sampling rates. For a moment, let's talk about sampling error. Sampling error is what we're trying to avoid by picking the right sampling rate. If we look at the graph on the right, this is a sine wave, which is a very pure input, very predictable. If we place 10 points on a sine wave, so let's say it's a 1000 hertz sine wave sampled at 10,000 times, you can see that it will not perfectly represent that sine wave. In fact, we can miss the peak values by up to 5%. And so how do you minimize sampling error? The simple advice is sample faster. Sampling faster means there are more points used to represent the curve. If we represent sampling error versus the ratio of frequency input to sampling, it looks like this. So on the left, that's simply a percentage of error on the peak values, and on the bottom, on the x-axis, that's the ratio between the sampling rate and the input waveform. In this case, at 10 to 1, so 10,000 samples per second at 1K data rate, you can see we're right at 5%. If we increase that simply to 20,000 samples per second, we drop to only 1% roughly. So what do you do? How do you make decisions for your testing environment? Number one is you need to determine the required frequency range or the bandwidth you're going to have to measure. And if you're working to a test protocol, many of those are very clear if it's automotive, aerospace, or biomechanics. Sometimes long, slow tests can use lower sampling rates, but you have to be careful. You need to think about what data bandwidth you really need. It's the first question I ask when I say I'm going to put instrumentation on a test. And then high-speed tests benefit from higher sampling rates. These days, there's no penalty for sampling at a higher rate. There simply isn't. Memory in computers used to be an issue. It's not an issue today. I took a 25-second video of something the other day and it was 85 megabytes. So that's nothing compared, the data is nothing compared to that. Number two, sample at least 10 times the highest frequency of interest. 20 times is better. When I'm doing tests in the lab and I want the highest possible data fidelity, I actually use 50 to 1. And again, there's no penalty. You're not going to run out of memory, which is a great thing. And third, a proper anti-alias filter is essential. You need a filter, and this is discussed in great detail to avoid aliasing. You can look back at principles of dynamic data collection and learn more about that. But you need a filter of at least 4 poles. It's good practice to set the filter at 1/5 of the sampling rate, and all of our software automatically defaults to using 1/5. Now, for those of you who want to adjust that relationship, there is a way to do it. We actually have a Help Center article that tells you how to pick the sampling rate and filter combination. Sometimes that's important to meet legacy requirements. What about recording modes? I don't have a lot of time to go into all of the possibilities here, but all of our systems have multiple ways you can store data to the memory when you're actually collecting data. It's important to match the recording mode to the test. For destructive tests, we always recommend what we call recorder mode. We literally start the device recording, and if we get a trigger or a time alignment event, great. And if we somehow miss that, we still have the data stored in memory. That's what recorder mode means. A lot of people don't look into don't look at the user's manual or don't look at the options in the software. We have multiple event modes available. So if you're going to do a test where you want to do 20 of this or 10 of that, we have modes where you can arm the data recorder, and then it will take data when you get an event, rearm immediately, and then be ready to take data again without going through the diagnostics. This can be important for lots of different tests. And then we also have a lot of auto-arm modes available. Now, what is auto-arm? Auto-arm means that you perform a setup, just like we've talked about setting up the sensors, picking the right sampling rates and all that. You perform the diagnostics and you arm for collection, and then you literally turn the system off. The setup parameters are stored in the flash memory inside the unit, and the next time you apply power, the data recorder loads its firmware, loads its collection parameters, and it's ready to use. This is important if you're going to go out and do a field test, and you don't want to have to plug a PC in all the time. So very important. Our hardware supports that, the software supports it, and if you find that helpful, then sometimes that's very helpful in extreme environments, particularly destructive environments with a lot of safety protocols. Just a few words about grounding and shielding, and I'm going to say just do it. There's more discussion about this in the Principles of Dynamic Data Collection seminars, webinars, but the bottom line is you must use proper grounding and shielding techniques if you want the highest quality data. This diagram shows that you will have a ground wire connected between, in this case, the mounting plate of the data recorder off to whatever I've got instrumented with sensors. So I have a ground cable to another device over here, and then we're using a nice shielded cable. So all this cable has what we call shields that are terminated to the data recorder side and not at the sensor side. If we do this, we will eliminate most of the problems that come with noise, potential data anomalies from electrostatic discharge, and so on. Again, more information about this in the other webinars. So let's just talk about the fact that we work in a lot of different fields, and all of this setup information we're talking about here is maybe implemented in different ways. Now, I got my start crash testing cars in 1979, and so that's kind of been our bread and butter business as we started. But we also are doing a lot of work these days in human-rated space capsules. That's both structural and human protection. We're also doing a lot more in-flight testing. If you were tuned in for the webinar on our new Slice Air system, you see we're getting much more into flight testing. Our products are well suited to placing them in interesting places like wind turbines. We're involved a lot with head protection studies, helmet studies, and sports, and then a little bit of work in the robotics world. So pretty interesting world. And I would say that these applications sort of highlight the fact that you need to learn how to set the data recorders up in different ways. And You might have odd sensors that you've never worked with before. You might need to use the auto arm modes or different recording modes. So we're here to help. And our Help Center is a great resource. If you go to dtsweb.com, and on the right-hand side of the screen, you'll see a little tab that says Help Center. And if you click on that, that will take you to the homepage of the Help Center. If you are not logged in as a registered user, you still have access to a lot of helpful information. You can use the search box here, just type in, RTD, thermocouple, sampling rate, whatever you want to do, you get lots more information. And it's a very, very helpful device. If you register, if you're a registered user, there's a box on there that says new or need support. If you're not registered, register, and then you can submit questions. And if you need specific things to download, we can give you appropriate access. So with that, what I'd like to do is we had while we're starting to get the Q&A going here, I'd like to take a little bit of a poll here. I have a simple 2-question poll, and I would appreciate it if you can see that. Maybe give me some answers there. The first question is, did you attend either part 1 or part 2 of the webinar on principles of dynamic data collection? And the second one is, are you currently using a DTS data recorder? Yes, no, or thinking about it. And that'll just be helpful. I'll give it a 30 seconds or so here, and then I'll launch that and let you see the results. I see they're coming in. We're 40 seconds into the poll. And how are we doing on the Q&A, guys? I have not been monitoring the Q&A, so at some point I'm gonna yield to the folks that might be able to answer your questions. Okay. I see a couple of polling answers still coming in. Okay, I'm going to end it right there, and I'm going to share the results. Okay. So it looks like a lot of folks here attended the Principles of Dynamic Data Collection webinar. That's really excellent, and a lot of you are current DTS users, and some aren't, and some are thinking about it. So really appreciate your polling input. And again, we're here for you. So I'm gonna stop sharing those results, and I'm going to actually take a look at the Q&A window here. Hey, any questions coming in at all? We're happy to, and even if it's a very specific question about how to hook up an odd sensor or something about anything we've covered here, happy to answer.
Hey, Mike, also, we're at time, but we will leave this open to answer any questions for those that want to ask. Click on the Q&A button at the bottom of the window and submit to Mike in our panel, and we'll do our best to get everything answered before we shut down here.
Yeah, and I'd also like to add that there's so much to learn in this field in order to be a true expert. And I chose some topics today that come up a lot in Help Center questions. And that is really understanding how the data recorder interfaces with the sensors in the world. But we would love to hear whether you thought this was helpful. Did we hit the mark? Are there any things you'd like to hear about in the future? I'm quite certain we will be doing more of these, and we will tailor them to any feedback we get from our users. So I really appreciate that. Question, when is the new SAJ211 going to be released? I'm going to answer that live. I think we're close, and later this year, as far as I can tell. So DTS, several of the DTS staff members are on the SA Instrumentation Standards Committee, And we've been working on a revised version of SAJ211 for several years. It was last updated in 2014. Like I mentioned, a key part of it is we're increasing our sampling rate recommendations and other things. So I see a couple of questions coming in, and we will, I think we're gonna, Jim, are we about ready to close it off here? Oh, here we go. Great question I can answer right off the top here. We had a question asking, will the older TDOS Pro support the new SAJ211? The answer is yes. Even though TDOS Pro was developed between 1997 and about 1999, it will absolutely support the new SAJ211. TDOS Pro modules are, for their entire lifetime, have been able to sample all 8 channels at up to 38,000 samples per second per channel. So, and the filters meet all the requirements for the new, any new J211. So yes, no sweat there.
Okay, Mike, I think we're pretty much at time. Appreciate everyone's attendance. For the questions that did not get answered, we will follow up directly with you and get answers to you. If there's any additional information you need from Mike and the support team, or from your sales team relative to any particular application questions, that's what we're here for. So please reach out. Please look for future webinars. We're going to continue this series throughout the summer and perhaps beyond. And again, appreciate your time and attention today. Thanks for attending, and we'll see you next time. Thank you.
Thank you so much.